Welcome, friends, to another episode in DEKB7QHC. I am going to present something that is marginally mystical, even existential. And it's all about resistors. Resistors at the very base level. Well, not even about resistors, actually. It's about noise that we see across resistors and that we call resistor noise. That's a misapplication of terminology. Actually, it's called thermionic noise or thermal noise. Thermionic is another term. Thermal noise. Let's see where that comes from. Here we see the cosmic microwave background radiation field that's been studied by various instruments in outer space, and it gives us the complete universe 360-degree view of in all directions. I guess there's only one direction for 360, but the total sphere of space around us varies in temperature by very minute amounts. Here the dark blue to the greens to the yellows to the reds, those are only temperature differences between those regions on the order of millikelvin degrees. So 1/1000th of a degree variation. This entire map probably exhibits no more than, well, I'll hazard a guess of 10 thousandths of a degree variation across the entire universe. But it's interesting for its clumping. Now, what's this have to do with us? Or a resistor, much less. Well, it has nothing to do with, well, it has everything to do with a resistor, because that resistor is part of the universe, as are you and I, and the ham shack around me, and the earth outside. All of this sits in a soup of noise that comes from heat, and that's as far as this goes, this is above absolute zero. So this is really cold and varying by thousandths of a degree. Not very much. Now, again, what's this all mean about resistors? Passive networks, even tuned cavities, resonators, all of them exhibit some thermal noise, and it's restricted in frequencies for those elements. They're naturally resonant, so they have a restriction of bandwidth. And that bandwidth is very important to the nature of the resistor and the thermal noise, because thermal noise is measured in voltage or current. Most often you'll see it in voltage terms or in power terms. And we're going to see them both here as I investigate. Our classic 50 ohm load, or the 50 ohm input impedance to a receiver, or much less the 50 ohm output impedance of a transmitter, all of these 50 ohm references follow here. We get off the cosmic microwave background here for a second, and we'll look at a 50 ohm load in an environment of 300 degrees Kelvin. 300 degrees Kelvin is about, it's going to be fairly, let's jump back to the studio here. 300 degrees Kelvin is just a engineering shorthand for room temperature here, although it's going to be a very warm room. This is fixed in the relationship between degrees Kelvin and degrees centigrade. So Kelvin has equal increments as a centigrade scale, but starts vastly lower at what we consider to be absolute zero. And that is not the zero of the centigrade scales. That's about 273 degrees above absolute zero. So there's a difference of 273 degrees. And if we were to add in temperature here, it's about 20 Celsius, maybe 21, certainly not 22, but not 30 degrees more, much as 27 degrees more for a 300 degree ambient. But as I said, 300 degrees, that's just a technical selection for simplicity's sake and close enough for our work. So, this resistor is sitting in a 300 degree Kelvin bath of heat, and it's going to see minus 174 dBm of that heat rendered into 1 nanovolt in a 1 hertz bandwidth measurement. So you'll see the equations at the bottom that support all this discussion. The Vn is noise voltage, and that's equal to the square root of 4 kBTR delta F. And we have power noise is equal to simply KT delta F. KB is a 1.38 times 10 to the minus 23rd joules per Kelvin. So using joules, that converts to watts. Kelvin cancels out with temperature, and a frequency takes care of the time element to turn this joules into watts. So, having said that, what else can I say? Okay, 1 nanovolt is the classic 50 ohm presentation of a 1 hertz bandwidth signal in a field of minus 174 dBm of noise. This is RMS. Now, if I were to change the bandwidth to 100 hertz, we'd go from 1 nanovolt up to 10 nanovolts. And the 100 hertz bandwidth imposes us with a minus 154 dBm noise level. This is the power, this is the voltage, this is the bandwidth of this system over here. 100 hertz bandwidth, you say 1 hertz bandwidth is almost impossible to use. 100 hertz, why did I select that? That relates to if you're doing CW, you need some sort of bandwidth to hear the other side, and you need a certain amount of bandwidth if they're coding at a fast speed. This fast speed is related much as rise time and bandwidth are related, and that means that you need an appreciably wider bandwidth to catch the faster CW. So I chose 100 hertz. That's strictly arbitrary. You can choose other values. The math on this board here reveals exactly all the components that go there. The 154 dBm, minus 154, that's 154 decibels below 1 milliwatt. This is extremely, extremely low voltage, low power. However, let's put it into an application that's more typical. This arrangement that I'm showing is more typical of a receiver listening to a 50 ohm load, such as an antenna may be at that frequency of choice. It's resistive, but that doesn't matter. The bandwidth that we do care about, well, if I were to say 5,000 hertz, that's the standard AM content of an AM transmission on the commercial bands. We in the amateur radio frequency, we in the amateur radio community use a narrower communication channels. The widest would be 3.5 kilohertz. You're really stretching the limits of intelligibility if you go much below, say, 2 kilohertz or even 1 kilohertz. So my choice of 5 kilohertz is for comfortable listening and to observe what kind of noise levels that we would have. So here at a 5,000 hertz bandwidth, that's going to bring us, that opens us up to more noise. And that is a total amount of 137 dBm down. This will give us across a 50 ohm source, our antenna, of 64 nanovolts RMS. There's absolutely no way you can escape this. There's no way you can escape this except through massive averaging. Unfortunately, we're not in a sphere where we can average a signal that's always changing. So we have to take the noise, the good with the bad. So returning to my application here, if I change the characteristics one more time, let's see what happens when we reach way high for a 1 megohm situation. Imagine that you're listening to a long wire antenna raw connection right to the first RF amplifier. There's no 50 ohm load that's been, well, we've removed. How do you get a 1 million ohm resistance from an antenna? Well, you don't really, because you still have a 50 ohm input impedance. If you could in fact achieve, well, let's just say that this is no longer a receiver, but as a oscope. And your oscope is looking at a 1 million ohm resistor. Itself has roughly 1 million ohms input impedance. So everything's pretty well balanced in that regard. Limiting it to a 5,000 ohm or 5,000 hertz bandwidth is not something that you achieve using an oscilloscope on its own, but if you pass this through a filter, yeah, certainly, you'd have to have a matching of that filter to the 1 million ohm resistance. That's it's achievable, but here we're gonna. I'll just go back to the chalk and talk, and here we can see of that 137 dBm down, it develops 10 microvolts RMS of noise across the resistor. This 5,000 hertz bandwidth is responsible for this figure up here. This figure is impressed upon this resistor here, which yields this voltage over here. So this is identical to the previous with just a 50 ohm, 64 nanovolt rendering of that same level of noise, and a very much higher 10 microvolts. 10 microvolts is at 5,000 hertz at your front end, your receiver that is going to be a heavy burden to carry. But we don't have 1 megohm input impedances. We don't have 1 megohm sources of signal typically in our applications. We can get into these kinds of situations by other means. That's what ham radio is all about, is experimenting and seeing, can you challenge my numbers in actual performance? And that's the importance of this discussion is, well, performance. Let's look at one other telling factor here. And I'm going to go lower in resistance to see what happens in that regards, but I'm going to choose one particular resistance that's meaningful, but not immediately so. And that's going to be with 8 ohms. Now, I still have the same bandwidth, 5,000 hertz. I have now an 8 ohm resistor instead of the former 1 megohm, or instead of that, the former 50 ohms. So this is a fourth of that. And it renders 26 nanovolts RMS noise across 5,000 hertz. So it's it's a wideband noise figure. It's just noise, uncorrelated. Now that 26 nanovolts is, for all practical purposes, is no noise whatever. There's very few bench instruments that you can use to measure nanovolts without some form of amplification and noise limiting in its own regard, because whatever amplifier that you add to the measurement of that noise voltage, you're injecting more noise, probably more noise than was in the original resistor, because it's a wider bandwidth amplifier. So we have challenges of restricting bandwidth in the entire chain of measurement. And this is what makes noise figure so important. Noise figure is typically found in equipment that's in the higher frequencies, or for premium equipment, like what you see behind me, especially, oh goodness, I don't know if I can, oh yes, the R390, yes. Its noise floor is just stunning. And the limitation of its performance is, in fact, found in thermal noise. So that's the nature of the importance of this. But I did say that this was somewhat mystical and somewhat existential. And what in the world are you talking about there, Richard? Because it seems all very ordinary. If I return to this again, and I'm looking at this 8 ohm resistor again, later that will be, I'll relate its importance. But the point of the matter is the power, noise power, is related to temperature and frequency. This is a constant. KB is this constant right here. Changes not one iota under any circumstance. So this is the ever-present, omnipresent, everywhere present power that's just soaking into us all. Especially if you turn up the heater like mine just did in the back corner there. You may or may not have heard of that, but the resistor merely reveals this noise. It's not the source of the noise. The heat is. The heat is the movement of electrons bumping into each other, going off in different directions, bouncing through this space. It's the agitation of life. The resistor is merely let's say it's the shadow to the sun of all this noise. And we can measure that shadow as either current, using instrumentation, or voltage across the resistance as instrumentation. Tuned circuits come with their own bandwidth, so that they're somewhat limiting in the amount of noise that they will support, shadow, as it were, because the noise is there. The noise is there. The noise is everywhere. But it's the resistance, the components that actually bring it into our circuits such that we suffer from it. And Claude Shannon did an interesting curve 70 years ago on the signal-to-noise ratio and how much error that brings to any measurement. That's pretty complex, but basically this definitely relates to digital representations, and we're back to keying CW again. Okay, I'm wandering here. It's probably getting over many of my listeners' heads, but I promise I'll cover this in sufficient detail in other discussions, and we'll move on to the significance of that 8 ohms. 8 ohms now. I'm sure that many of my listeners are, their ears are already peaked with that number specifically. This is the impedance of a speaker. Now, 8 ohms, you might well say, well, it's not a resistor, Richard, it's a speaker. Yes, it is a speaker. It has a coil. We might reasonably presume that it's inductive, but that's not the way it works. It's a piston, and it dissipates heat from work. So it has a noise level. I showed you that, 20-odd nanovolts, something that few, if any of you, I can't even measure that in my current circumstance, so I know that you're unlikely to. How is this a problem? Well, it isn't a problem unless you have, okay, what are you driving the speaker with? Okay, certainly a signal that's much greater than 20-odd nanovolts. Now, if you were to connect the classic tuned circuit with a crystal rectifier, okay, substitute a diode, right into this loudspeaker, then you capped the loudspeaker with a little hose that came up to your ear, you could easily DX the world if you're tuning that crystal circuit. Yeah, it's been done. The power levels that you receive raw from your antenna through a tuned circuit to a diode, a rectifier, immediately into a speaker, nothing else. The power that you received is sufficient to drive the speaker so that you can hear it in, let's say, a quiet environment. All of those are related in decibels and dBms, and a lot of math goes into proving this. Performance proves it equally well, so we can move on from there. So that was my choice for 8 ohms, and showing you the noise floor for that particular receiver. If my classic back here needs to be outclassed, I just did it with a speaker. However, it doesn't have that, the tuning is a little bit rough, but that's rambling. So I'm gonna end it here, and I hope that the existential part of this is it's the function of the resistor is to prove that there's noise. So that's the existence. My body here supports the revealing of noise. I hope this isn't, well, okay, enough. 73's friends. I hope to see you in future episodes.